Good evening, boys and girls, and welcome to another lesson of Technical Sciences Grade 12. And today, for a change, we are doing paper 2, and this is organic chemistry, a very, very critical topic in paper 2 because it carries so many marks, right? I can tell you now that this particular topic carries 85 marks for your preparatory examination. 85 marks, so that is close to about 60% of the question paper will be on organic chemistry for paper 2. And that is why in preparation for your examinations, I decided that we definitely need to look into organic chemistry so that you are well prepared for your organic chemistry questions when you are dealing with paper 2. So let us get right into it and actually look at what is expected of you in terms of examination guidelines for this particular topic. Now, the outline of the lesson today will be an overview on organic chemistry, so it's nomenclature that we are going to focus on today, because this section is actually divided into 3. We have nomenclature of organic compounds, then we have physical properties of organic compounds, and lastly we have reactions of organic compounds. So for today, we are going to look into nomenclature of organic compounds. And in nomenclature of organic compounds, we are going to focus on the different homologous series, but for today only it will just be alkanes, alkenes, as well as alkynes. And features of the topic, my dear learners, we are definitely going to look at nomenclature holistically. And then for our assignment, we are going to look at questions on nomenclature. And in terms of the topic, we'll also look at how you need to prepare yourself for the examination. Right. So let us look into organic molecules and look at nomenclature of these organic molecules. And I am taking you through what the examination guidelines require of us to know in preparation for our upcoming preparatory examination as well as the final examination. So we must be able to define organic molecules as molecules containing carbon atoms. Now, I want you to remember that, my dear learners, because we will talk quite a lot on that. And you know, with the issue of time, my dear learners, I didn't want us to actually just write out the definitions and so on. We have them in our examination guidelines, so let us remember them. And now and again, we will refer to those particular definitions all together. Right. So firstly, we must be able to define that term, which is organic molecules. And furthermore, we must be able to write down the molecular and structural formulae of organic compounds, but we are going to end up to 6 carbons. So we won't be looking at molecules that go beyond 6 carbons. So we will be dealing with that. And when you talk about 6 carbons in this case, my dear learners, we are just saying the longest chain without breaking, or what we then refer to as the parent chain. The parent chain will not be more than 6 carbons. But remember now, it can still be more than 6 carbons, but other carbons can then be part of what we refer to as the substituents, or what we refer to as alkyl groups. But the parent chain, the longest chain without breaking, will definitely be 6 carbons. And then we are going to look at different homologous series. Now, my dear learners, I take it now that you do know what I'm talking about when I talk about homologous series, because you have done this topic by now. And when we refer to homologous series, by definition, you will remember that it is a series of organic molecules that can be described by the same general formula and where each member differs from the next by a CH2 group. So it's a series of organic molecules that can be described by the same general formula and where each member differs from the next by a CH2 group. Now, we have different homologous series. Now, the homologous series that we are going to focus on are our alkanes, are our alkenes, our alkynes, our alkyl halides, what we also refer to as haloalkanes. What we refer to as haloalkanes. Then we look at aldehydes, then we will look at ketones, and then we will look at alcohols, and we will also look at carboxylic acids. Now, what is critical as well, my dear learners, is I know you are using different types of textbooks and they have a lot of information, but remember, my dear learners, we are not going to deal with ring structures. Basically, we are not going to deal with cyclic structures. And the same will apply to alkenes. We won't be dealing with ring structures. But then when we look at haloalkanes, we will then be able to differentiate between primary haloalkanes, secondary haloalkanes, and tertiary haloalkanes. But we also won't be looking at ring structures. And then again for alcohols, we will be looking at primary alcohols, secondary alcohols, as well as tertiary alcohols. So that is what we'll be doing, and most probably that is going to be tomorrow. Right, and I'm hoping that as I'm telling you what you need to know, you're actually getting very excited to say, but I know this one, I know this one, I know this one. And where we have challenges, remember then, it is then that time where you are able to send questions to our emails, which I will give to you to copy down at the end of this particular lesson, so that you are able to then send me questions and I will definitely be able to assist you. Then we will then distinguish between different homologous series. Then we must be able to talk about saturated as well as unsaturated hydrocarbons. We must talk about 6 carbon long atoms, or rather 6 carbon long organic compounds that are made up of carbon, and those that are saturated and those that are unsaturated, as well as isomers, or what we then refer to as structural isomers. And we must know the general formulae of different homologous series. In other words, we must know what is the general formula for alkanes, the general formula for alkenes, alkynes, haloalkanes, aldehydes, ketones, carboxylic acids, etc. Then we must be able to define the term hydrocarbons. We must be able to define the term hydrocarbons. And I will also be able to show you keywords in between. And we define that as organic compounds that consist of hydrogen and carbon only. So that only, there is also a critical word, but we will talk further about that. Then in our hydrocarbons, we must be able to differentiate them between saturated hydrocarbons as well as unsaturated hydrocarbons. So we have those that are saturated altogether, and we say those contain only single covalent bonds between carbon atoms. And then we have unsaturated compounds, and they contain double or triple bonds between the carbon atoms. So it's also going to be very critical because we will be emphasizing what do we mean when we say they are unsaturated, and we'll then look at the structures to then be able to really see what we mean when we say they are unsaturated. Furthermore, we must know the following definitions, or what we call them terms. And we have a term there, we refer to it as a functional group. And from our previous knowledge, my dear learners, we know that each and every homologous series has its own functional group. So we know it is an atom or a group of atoms that determine the chemistry of a molecule. Or it is an atom or a group of atoms that determine the physical and chemical properties of a group of organic compounds. So we will talk about that, and perhaps we will, engage further in terms of this, because a functional group also includes a bond altogether. So it's actually an atom or a group of atoms or a bond that determines the chemistry of a molecule, or alternatively, that definition that you see there. Now, my dear learners, as we go through the lesson, I don't want you to be confused. Remember now, sometimes we refer to organic compounds, or sometimes we refer to organic molecules. So where I talk about organic compounds and where I talk about organic molecules, just know that I am talking about the same thing, right? I could then be saying organic molecules, or I could then be saying organic compounds. So it is the same thing. Even in your questions, be aware that if they refer to organic molecules or organic compounds, they are talking about the same thing. And then that definition of a homologous series, which I have already given to you, and we said it's a series of organic compounds that can be described by the same general formula, and where each member differs from the next by a CH2 group. And we will definitely engage further on that. So my dear learners, a good reminder of what you are expected to know in this particular topic. Then here we have a table, and this table is there in your examination guidelines. It is so important because this forms the basis of learning organic chemistry, because it shows you the different homologous series, and it shows you the structure of the functional group. In other words, what do you look at that shows you that this is an alkane? What do you look at that shows you that this is an alkene? And you look at the functional group, and this is the structure of the functional group. In other words, how do you see alkenes? You will see them by the fact that they have a double bond between carbon and carbon atoms. How do you see alkynes? They have a triple bond between carbon and carbon atoms. How do you see alcohols, for example? They have a hydroxyl group bonded to a carbon, which is that OH. So that is what the functional group is. What you actually look at, that shows you what this molecule is. And we also must then be able to give the names of these particular functional group. And where we don't have a name, it means it is definitely not necessary for us to know that. Altogether, my dear learners, so this is basically something that forms the basis of learning organic chemistry, and we will engage on that as we continue with our lessons for the week. Then the same applies to your aldehydes and ketones and carboxylic acids and esters, etc. We must know the functional groups, how to draw the actual structure, and also the name of these functional groups. Now, furthermore, when we are given structural formulae, we must then be able to give isomers, Basically, if I give you, for example, a structure like butane, I can ask you to draw an isomer of butane, a structural isomer of butane, and from then I can also ask you to give the name of that structural isomer of butane. So it's very important, my dear learners, that you understand each and everything that we are telling you here, because 85 marks is a lot, and it really gives us a chance to assess you on everything. So here we are definitely not going to skip anything, and I want you to be very confident as we go through this particular lesson, so that you better yourself and you learn this particular topic and you do well. Right. And when we'll also be drawing this structural formulae, and remember now, when you talk about this structural formulae, they show which atoms are attached to which. In other words, which atoms are bonded to which, and we are going to use lines to show those covalent bonds and so on altogether. And then we must be able to define what a structural isomer is. What a structural isomer is. And remember, my dear learners, sometimes instead of saying structural isomer, we could simply say to you, define the term isomer. And it means the same thing. So this is a definition for an isomer, and this is a definition for an structural isomer. It is the same thing, and we can ask it in either way. And remember again, all isomers are structural isomers, and that is why the definition of an isomer is still a definition of a structural isomer. But what you will then know is that we have different types of isomers, or different types of structural isomers, which are these ones. We have those that we call chain isomers, then we have positional isomers, and we also have what we call functional isomers. So we must be able to work with all of those altogether to say, okay, what type of isomers are these? Let's say I gave you two structures and I ask you, what type of isomers are these? You must then be able to tell me the type of isomers, either chain isomers, positional isomers, or either functional isomers. Right. Then we will engage further on the examples of chain isomers, but we must be able to also define what a chain isomer is. So all the definitions I am highlighting for you. And you see, these are quite a number of definitions, and it is very important that you know them. And these are just the definitions under nomenclature. Right. So those are isomers that have the same molecular formula but different types of chains, and we will talk more about that. Then we also have positional isomers, and we say they are organic molecules that have the same molecular formula but different position of the side chain, substituents, or functional groups on the parent chain altogether. And you can choose any, so I will just simplify it for you so that it becomes quite easier for you. Right. Then we are going to learn IUPAC naming and formulae. So we must be able to give a name to an organic compound if we are asked to do so, and we are going to follow the rules. And the rules, my dear learners, it's something that we need to put in our head and apply at all material times when we are giving definitions. Right. So we must be able to write down the IUPAC name when given the structural formulae for all these homologous series altogether. Right. Furthermore, we must be able to write down the structural formula when an IUPAC name of all this homologous series has been given. In other words, we must be able to move in between. If I am given a structural formula, I must be able to give an IUPAC name. If I am given an IUPAC name, then I must be able to give a structural formula. Then we must be able to identify alkyl substituents, right? Methyl and ethyl, and we'll talk about that, in a chain to a maximum of 2 alkyl substituents on the parent chain. And then when naming haloalkanes, the halogen atoms do not get preference over alkyl groups. Numbering should start from the end nearest to the first substituent, either the alkyl group or the halogen. In haloalkanes, where, for example, a Br and a Cl have the same number, when numbered from different ends of the chain, Br gets alphabetical preference, and so on altogether. And when an alkyl group is a substituent in a molecule, it should be treated as a substituent. And we are definitely just being reminded here of some of the IUPAC rules that we will apply. For example, when we write IUPAC names, substituents appear as prefixes written alphabetically, like your bromo, chloro, ethyl, methyl, ignoring the prefixes di and tri. So those are good, or rather the main IUPAC rules that we are going to follow when we deal with naming of organic molecules, basically giving them IUPAC names. Then we get to the main part of our lesson, and now we look at alkanes. Now, alkanes, they are compounds consisting of single stable covalent bonds between carbon and carbon atoms, and naturally they have a low reactivity. And I'm just reminding you there because it will help you when we start to deal with organic reactions. Now, why? When we perform the reactions, for example, we need to provide heat as well as have the reaction under a higher pressure. So we will talk about that, but basically when you look at alkanes, you will see that they do consist of single stable covalent bonds that you get between carbon and carbon atoms. Now, the functional group of alkanes is this one, is this particular structure. Now, when you draw a functional group, you actually want to show us that, okay, the homologous series is alkanes. Remember, my dear learners, this is the homologous series. It's something like a family. It's just that we have a scientific term for that family, and the scientific term for the family is what we call a homologous series. So we don't say family, we say homologous series. Now, in this homologous series, a functional group, basically, just to make it easy for you, it's something that you look at that tells you that this belongs to alkanes. Now, when you want to see that a substance is an alkane, you expect to see single bonds between carbon and carbon atoms. So there's a carbon atom, there's a carbon atom, and you have a single bond between carbon and carbon atoms. So that's what you will do. From doing that, when you draw a functional group, you must make sure that around each carbon you have 4 bonds. Why? Because carbon is capable of making 4 bonds. So the first bond that you show us is that single bond between carbon and carbon atoms. So on this carbon, I have the first bond, then I have the second bond, then I have the third bond, and then I have the fourth bond. On this other carbon atom, the first bond is still this one to the other carbon, the second bond there, the third bond there, and the fourth bond there. When I have done that, I know that I am going to get 2 marks. Why? Because I have shown them that if I want to see an alkane, I want to draw its functional group. I want to see the functional group. And what will show me that this is an alkane is a functional group where the carbon only has single bonds between other carbon atoms, or rather with other carbon atoms. So the aim is to show us that single bond between carbon and carbon atoms. But furthermore, the aim is to then show us that there must be at least 4 bonds between carbon atoms. And furthermore, my dear learners, you do not include the hydrogens. You can't include the hydrogens, because now if you include the hydrogen, you are actually drawing the organic compound. You are actually drawing the organic molecule. So then you would have drawn ethane, and you wouldn't have drawn the functional groups. So if you include the hydrogens there, then you are going to forfeit your marks. It will be a 0 out of 2. Secondly, the general formula of alkanes, it's CnH2n plus 2, and the N there, it stands for the number of carbon atoms. So the N there stands for the number of carbon atoms. Now, what does this teach me? It teaches me that if I were to draw an organic molecule, for example, with 1 carbon, right? And it is an alkane. In other words, it is an alkane with 1 carbon atom. Then, according to the general formula, when I draw that molecule, it will be carbon, and remember there, the N stands for number of carbon atoms. It will be a 1, H2, and the N stands for number of carbon atoms, which is 1, plus the 2. Everything is a subscript there. In other words, it's C1, which is C, H, 2 multiplied by 1 is 2, plus 2 is 4. So it means if I have a molecule with 1 carbon, then it will have 4 hydrogens. And that is definitely correct. Because if I have a carbon there, remember carbon must make 4 bonds, so it will be 1, 2, 3, 4. And to fulfill or to fill up my molecule, I can see that the general formula tells me that I have to fill it up with hydrogens. So I will have 1, 2, 3, 4 hydrogens. And why is it 4 hydrogens? Because each carbon must make 4 bonds. So it's 1, 2, 3, 4 altogether. So that is 1 molecule there. So it is defined by that general formula. Now let us try another one. Let us say I have a molecule with 2 carbons. The general formula, it's CnH2n plus 2. In other words, I'm dealing with an alkane that has 2 carbon atoms. Then it will be C. Where I see N, it means it is the number of carbon atoms, it's 2. Then it will be H. Then we will have 2, and that 2 will be multiplied by that N, which represents the number of carbon atoms, which is 2 plus 2. Then this will give me C2H. Then I will say 2 multiplied by 2 gives me 4. And then 4 plus 2 gives me 6. In other words, any alkane that has 2 carbon atoms, it must have 6 hydrogen atoms. Now, how do I draw that? Remember, now I have 2 carbon atoms. So I'll have the first carbon there, and then I will have another carbon there. Now, what do we know? We know that if it is an alkane, it has single stable covalent bonds between carbon and carbon atoms. So because it's an alkane, it means between the carbon atoms, I have a single bond. Then what must I do now? I must know that around each carbon, I need to put the hydrogens. And I must make sure that each carbon has 4 bonds. So this will be the first bond, so the second bond, the third bond, the fourth bond. The first bond, rather, the first one is this one, the second bond, the third bond, and then the third bond. And then it shows me that it must be 2 carbons and 6 hydrogens. It means the other remaining bonds means that I have to put my hydrogens. Then hydrogen number 1, hydrogen number 2, hydrogen number 3, hydrogen number 4, hydrogen number 5, hydrogen number 6. And we are definitely happy that we are getting 2 carbons and 6 hydrogens. Now, what are we learning from this? We are learning that these 2 molecules, they belong to the same homologous series. And why are we saying they belong to the same homologous series? Because they are being defined by the same general formula. So if I use this general formula, I get that CH4. If I use that general formula, I get that C2H6. So these molecules are defined by the same homologous, rather by the same general formula, which is CnH2n plus 2. And because they are defined by the same general formula, we say they belong to the same homologous series. Now, I want you to check here. They are belonging to the same homologous series because they are defined by the same general formula. And what else can you see? Can you see molecule number 1, the first molecule with 1 carbon? How does it differ with the next molecule which has 2 carbons? So I'm comparing a molecule that has 1 carbon to a molecule that has 2 carbons. So if I'm doing that, what is the difference here? The difference is that here I have 1 carbon, here I have 2 carbons. In other words, the first difference is the fact that they differ by 1 carbon. Then here I have 4 hydrogens, but there I have 6 hydrogens. So what is the difference between these two? The difference is that they differ by 2 hydrogens altogether. Now, these molecules, these 2 molecules, they have the same general formula, but this member and this member, which are members next from each other, 2 carbons to 1 carbon or 1 carbon, then the next one is 2, then they differ by what we call a CH2 group. In other words, my dear learners, this is exactly how we define the term homologous series. Homologous series, basically, the general formula is the same, but the CH2 group is what makes them different. So these 2 molecules, my dear learners, they belong to the same homologous series. Why? Why do they belong to the same homologous series? Because they are described by the same general formula, but they differ from each other. They differ from the next by a CH2 group. And that is essentially what the definition of homologous series means. And there it is. You see, homologous series, it's a series. Number one, you have to start it there. It's a series. And if this word is omitted, my dear learners, you are going to lose all the 2 marks. It's a series of organic compounds. Remember, you don't just say it's a series of compounds. It is a series of organic compounds. So those are keywords. And we saw that they can be described by the same general formula, and where each member differs from the next by a CH2 group. Are we together? Right. Then we go back. So that is the general formula, and this is the structure of the functional group. Now, my dear learners, I want us to look at these things. What we have here is the structure of the functional group, what you look at in order for you to identify an alkane, single bond between carbon and carbon atoms. What else can we say about these alkanes? We can say, okay, this is the structure of the functional group, then this here is what we refer to as a structural formulae. Right? This is what we refer to as a structural formulae. Okay, this is not a nice pen to use. Doesn't show nicely, the yellow. We'll try a different one. Let's just erase them. Let's go for that one. Africa Tin Geeks color. Right. This is what we call a structural formulae. Or if it is just one, we simply say the structural formula. So you must know that if we ask for the structural formula, my dear learners, you have to draw. It means you must draw that particular structure. So I have drawn that structure, and I will teach you naming, but that we call methane. So I have drawn, so I show the carbons and I show which atom is bonded to which. So this is a structural formula, and it's a structural formula of methane, but we'll talk about that. This as well is a structural formula altogether of the molecule of the organic compound, but this is the structural formula of the functional group. So what is the difference between this one and this one? Can you see this is the actual molecule? It's ethane. Hence, I've shown the hydrogens, but there I can't show the hydrogens because if I start to show the hydrogens, this is no longer a functional group, it's the actual molecule. So in a functional group, we do not show those hydrogens, but you will see as we go on, like in your aldehydes and so on, then I will show you why there we actually need to show those particular hydrogens. Are we together? Furthermore, I want you to note again that when you look at these molecules, right? Just want to make a space for myself there, or I'll just write it down there for you. We say these alkanes are saturated. Alkanes are saturated. And what do we mean when they are saturated? They are saturated Now, what do we mean they are saturated? Saturated means they contain only single bonds between carbon and carbon atoms. And my dear learners, it's very important that you mention that word only. They contain only single bonds between carbon and carbon atoms. Remember, when we go further, right, and you we look at alkenes, you will see that alkenes also have single bonds between carbon and carbon atoms, but it's not only single bonds, they also contain a double bond. So with alkanes, it is only single bonds between carbon and carbon atoms. And you don't just say only single bonds, because there is a single bond between the carbon and hydrogen. You must be specific that the single bonds are between carbon and carbon atoms, and it's only single bonds. Furthermore, my dear learners, we say alkanes are also hydrocarbons. So say, what do you mean when they say they are hydrocarbons? Can you see that word there, hydrocarbons, means that you can take that word and actually break it into two. Can you see that? You can actually break it into hydro, it gives you a guide. You can also break it into carbon. It is a hydrocarbon because it is an organic molecule, or those that are used to compound, it is an organic compound that contains only carbon and hydrogen atoms. So when you check here, my atoms are just carbons and hydrogens. When you check there, my atoms are just carbons as well as hydrogens. I don't have any other atoms. There's no oxygen, there's no chlorine, there's no halogen, there is nothing. It's only carbon and hydrogen atoms. And that word again, only, is critical, because if you say it's an organic molecule that contains carbon and hydrogen atoms and you stop there, you see that you did not include the word only. And if you didn't include the word only, it becomes wrong, because when you look at other organic molecules that we'll look at, for example, your aldehydes, they also have carbon and hydrogen atoms, but it's not only carbon and hydrogen atoms altogether. So you must be clear that hydrocarbons are organic molecules that contain carbon and hydrogen atoms only. And that is that. You see, they are organic compounds that consist of hydrogen and carbon atoms only. And then saturated hydrocarbons, they contain only single covalent bonds between carbon atoms. And can you see there, between carbon atoms is also very critical. So that is what you are supposed to know, and you are supposed to define in that particular fashion. Are we together? Now, we must be able to name alkanes. Now, when we name an alkane, you must know the name ends with ANE. So all alkanes, the name ends with ANE, and it's very simple. It's an alkane. So if it is an alkane, then the name ends with ANE. Then you look at the number of carbons. Now, if carbon is only one carbon, then I'm going to have my name begin with meth. Altogether, my name will begin with meth and it will end with ANE. So in other words, meth is when I have one carbon, and then because it's an alkane, then I'll give it ANE. For example, let us look at this molecule. How many carbons there? It's one. So my parent chain, the longest chain without breaking, only has one carbon, so it's a meth. And then it's an alkane, so it's ANE. So the name is then methane. And from recalling again, you will know that 2 carbons is F, 3 carbons is prop, 4 carbons it's but, 5 carbons it's pent, 6 carbons it's hex. So that is how you would name them. Let's check there. I have 2 carbons here, 1 carbon there, 1 carbon. So I have 2 carbons. So the name will begin with F. And then single bond between carbon and carbon atoms, it means this is an alkane. So if it is an alkane, then it will end with ane. So the name of this molecule is ethane. Then this one, I have 3 carbons long, so it means it will begin with prop. Single bonds only between carbon and carbon atoms, so it will end with ane. So this is then called propane altogether. So let us check there. This is what we refer to as an IUPAC name, that is the structural formulae, and that, my dear learners, represents the molecular formulae. So that represents the molecular formulae altogether. So that is the IUPAC name. This is the structural formula, and this one here is the molecular formulae. So when we talk to the molecular formulae, my dear learners, how does it differ from the structural formulae? The structural formulae, and this is just one, the structural formula shows which atoms are bonded to which. For example, the carbon is bonded to the hydrogen, is bonded to this carbon, and so on. So you draw the structure and you show the bonds. But with the molecular formula, all you do is you count how many carbons are there. So we can see it's 1, 2. So we say it's C2. Hydrogens, it's 1, 2, 3, 4, 5, 6. So the number of hydrogens, it's 6. So the molecular formula just shows you how many carbons are in that molecule and how many hydrogens are in that molecule. And for other molecules, it's simply to say it shows you how many of each atoms are present in that particular molecule. Are we together? Right. So this will then mark the end of the first lesson. The only thing that we will be looking into when we go into the second lesson is to look at isomerism of these alkanes, and we will be looking at butanes and more, and we'll also look into alkenes. But what I wanted to move to, at least for today, is just to give you tips on preparing for your examination. Remember now, my dear learners, for the preparatory examination, the entire organic chemistry, it will be 85 marks. That means the section on nomenclature of organic molecules, the section on physical properties, and the section on organic reactions. But this section alone, which is nomenclature, will be plus minus 29 marks. Right. I have definitely enjoyed the lesson for today, and I hope that you have done so too. Remember, if you have any questions that you want me to attend to, at least on a Saturday during our question and answer session, you can send those particular questions to STEM Digital School at africateamgeeks.co.za. And I will be able to help you with those questions. And if you send them today, I will still be able to help you tomorrow. Thank you so much, my dear learners. I hope you had a great time and enjoy the rest of the evening. Goodbye.